somebody said, well, who wants to do this shit job? And I said, I'll do it. So me and the tech, we went and fixed 100 boards. So we figured out what was going on with the test equipment. We figured out why the boards were failing in certain ways. And then, and that was really interesting because later on I was working on power supplies in a big fax computer, and I knew all about power supplies. Like, because I did a shit job and I got good at it and I figured out what was going on, then we were having this problem with power supplies in a big fax computer, and I was like, I know about power supplies.
Our guest today is Jim Keller, CTO of Tenstorrent AI processor startup. Jim is the legendary CPU designer revered throughout the engineering community as he worked at Digital Equipment, AMD, Apple, Intel, Tesla, and others. In this first episode, our conversation is focused on Jim's early career, including how he got his job at Digital Equipment. It's not what you think. And what he learned from Gordon Bell, who was CTO at Digital Equipment at that time. Our conversation then moves into Jim's observation of how the processor world has begun to change. Here's how my conversation with Jim started. Now, let's
just gonna wing it here, huh?
I know, I'm winging it.
Perfect.
Don't we all do that? I was just it's a pleasure, really. It's a pleasure to have you on this program. This program called Tech Vision, and we invite several guests who are executives who are in the know, in my opinion. Who have actually worked, walk the walk, talk the talk. I mean, in your case, I picked because you have gone through. Really, you lived through the history of processing world, right? And when you look at the things from what you had experienced with DEC, personal computers, Apple, Tesla, where you are. So really, the purpose of this discussion is that I want to start with the history of the processor and what's happening now and what will happen next. That's really the big picture. I'm just clipping you right now, but it's yes.
Yes, that's a big topic. And let's see. So I started working at Digital Equipment in 1982.
Yep.
That is officially 40. It'll be 42 years ago soon. And I graduated from college in 1980. And I had exactly 2 courses that were useful for computer architecture. One, I did programming on punch cards on an IBM 360. And the other is I had one logic design course where I learned Boolean algebra, Carnot maps, and very simple logic design. I thought I was going to be a semiconductor physics person in college.
Yeah.
So I took processing classes, and I knew about transistors and implants and all kinds of things about silicon characterization. But I didn't actually ever study computers, really, and I only had 2 vaguely useful courses about it. So,
are you saying that you actually learn everything on the job then? Pretty much.
So, and I've talked to students about this a number of times because periodically, there's new course curriculums, like, they want to do SoC design, or they want to do CAD tool design, or they teach students layout. I was an electrical engineer, which turns out to be an amazingly good discipline to learn for a long run, I have to say.
Yeah.
We did math, physics, real science at Penn State when I went to school back in 1976. We started the first year with mechanical engineering, statics and dynamics, calculus, chemistry, physics, There was this thing called weed out courses. So some of those first courses were difficult to find out if you could, really do engineering. And then electrical engineering itself, we did circuits, electromagnetic fields. There's some sophisticated math in electrical engineering, Laplace transforms, Fourier transforms, which helps you do circuit analysis. And then there was some amount of material science. And semiconductor courses were very good on physics and understanding how you go from abstract things like circuit analysis and electromagnetic fields to a device. Here's a physical thing.
Right.
And then Penn State also had a curriculum that required courses in humanities, philosophy. I was actually a double major in philosophy and electrical engineering.
Really?
Well, the sad story is I couldn't write. It turns out I'm very dyslexic. I didn't know that until I had children. But I couldn't write. And the philosophy department chair told me they were happy to have me as a student in their classes. They had never had an electrical engineer major in philosophy before.
Yeah.
But since I couldn't write, I would not get a philosophy degree from Penn State.
Oh.
So I got B's in philosophy, but that was charitable, because if you graded my papers, it was not good. And I think being dyslexic is an asset to me personally, because I can see things in my head that I can't write down, write about. So, but anyway, so electrical engineering was a very good major. And then sometimes I talk to students now who did computer science or EECS, and it tends to be much more application based and less fundamental theoretical.
Right.
And again, my curriculum, I had quite a few lab courses. We built circuits, we had to make them work. The problem with, circuit design and labs is nothing ever works like you thought it was going to. So by the time I graduated college, I could build circuits, analyze stuff, and I could go in lab and fix it and stuff. So I did a lot of stuff early in my career where the stuff I made, I actually built, and then I tested it and figured it out. And that turned out to be useful for computer design in general. So
interesting. So when you joined the first company was DEC, right? And
so I worked at a company called Harris, and I joined their fiber optics group, and I worked there for about a year and a half. Mm-hmm. And the project I was hired to work on got disbanded, and I ended up being a lab tech for a year and a half because they didn't have anything for me to do. And I fixed many computer systems. And I had to redesign several logic boards. Logic board used to be a board about this big with 50 parts on it. And they had a number of boards that didn't work, either because they were broken or because they were poorly designed. So I did about a year of tech work and, let's say, entry-level logic board design. And then something about that on my resume helped me get a job at Digital Equipment, working on the VAX 8800. So in 1982, I started in the VAX 8800 group, and the first two computer manuals I ever read were the 1170 manual and the 1170-80 manual, and I read them on the airplane on my way to the interview.
Wow.
So my introduction to computer architecture was two manuals a friend randomly gave me when he heard I was interviewing at DEC. So I read the manuals, and then I showed up to the interview with a lot of questions, because a lot of things in the manuals didn't make any sense, or some ideas I thought were dumb. So I
got you a job.
What's that? And that got me the job. Yeah, I'd sit down and they would have all these questions for me. And at some point I would say, I have a lot of questions for you too. And I'd pull out the manual and said, you guys said blah, blah, blah. This seems crazy. Why did you do it?
Yeah.
And I think they partly hired me because, I knew something about logic design and computer board design, but they also had never had a candidate that had so many questions about the manuals that he read. And one guy told me he thought it would be funny if they hired me. So, and his
So
name was,
it's like it's all hindsight, though. I mean, it's not like you had the best, well, you had a really good foundational education when you
yes, I did.
joined. You sort of went along with whatever you job you got to move on, right? I mean, it's
Yeah. And this is good advice for people, I'll say.
yeah.
Almost every job I've ever had, I decided I would take it seriously and do as well as I could and learn as much as I could. And I've had some very good jobs and I've had some not so good jobs. And I work with people who are like, I don't like my boss, I don't like my job. So then they spend a year doing a half-baked job. And then their career doesn't go very fast. Where I would be like, I was in this lab and we had all these broken. One of Harris had a contract. They bought a company that had a contract to do remote power controllers. So they had this board they would put near your junction box in your house that they could remotely turn off your air conditioning if there was too much power. This is back in the 80s, right? And the board was poorly designed. They didn't have good test equipment. It was viewed as a shit job. And and somebody said, well, who wants to do this shit job? And I said, I'll do it. So me and the tech, we went and fixed 100 boards. And we figured out what was going on with the test equipment. We figured out why the boards were failing in certain ways. And then, and that was really interesting because later on I was working on power supplies in a big fax computer. And I knew all about power supplies. Like, because I did a shit job and I got good at it, and I figured out what's going on, then we were having this problem with power supplies in a big VAX computer. And I was like, I know about power supplies. And so, we figured out why the power supplies were failing. And so,
So tell me the transition, though. It's not like you had the utopian idea what the mobile phone processor should look like, or what the autonomous vehicles, the full self-driving computer should look like. How do you make that transition? Did you have any idea that what needs to be fixed before you
yeah.
got the
So,
job?
yeah, this is a really good thing. So I got very lucky. I worked at Digital Equipment in the mid-range VAX group, and the chief architect was a guy named Bob Stewart, who was a brilliant architect, and he had worked on the 1144, the 1170, and 11780 before the VAX 8800. And he was a very good computer architect. And at the time, digital CTO was Gordon Bell. Now, Gordon Bell invented what became Bell's Law, which
Okay.
is every 10 years, computers get better enough that it enables a new kind of computer, right? So
Yep.
the two laws that drive computers, generally speaking, are Moore's law, which says twice as many transistors every 2 years, and Bell's law, which is every 10 years, you have more transistors to the point where you can make a new kind of computer. And he figured that out while working at Digital Equipment, because we went from mainframes to mini computers to workstations to PC to mobile. And that took about 50 years. And when we were working on the VAX 8800, the initial target of the VAX 8800 was to be faster than the 780. It wasn't, there's a curve of progress.
Huh.
But then Gordon Bell decided that it wasn't faster enough because the competition was moving. And then at some point he came and said, computer performance needs to improve on this curve. And so we adjusted our target for the VAX 8800, which we hit. We struggled on the next generation because there was a big transition from bipolar design to CMOS design. Like at the time we did the VAX 800, all the high-end computers were what's called ECL. So those bipolar transistors, emitter coupled logic, they were very fast transistors, but not very dense. And all the low-end designs and microprocessors and little tiny computers were made with CMOS, where the transistors were very small, but not very fast. And then it turns out, as the transistors got smaller, they naturally got faster, and CMOS caught up with ECL. And so the VAX 800 was the last great ECL computer that Digital built. And then all products after that were CMOS. And that caused a very big disruption. And that enabled the generation of Sun small servers and workstations. And Digital built Alpha, which was simultaneously the world's fastest computer and a business failure. And Digital went bankrupt. And so I would say at that time, I was a designer and a participant in it, and not, let's say, a leader of any thinking about it. Like, Gordon Bell's a genius, and Digital did very well while he was CTO, and Digital went bankrupt after he left. I think that's causal. If Gordon had stayed, Digital would have done better long term. Bob Stewart was a great architect, but he was a great architect in the era before microprocessors and, let's say massive numbers of transistors on a chip. The VAX 800 was like less than 1 million transistors, and modern computers are hundreds of millions of transistors. So
it turns out Bell's theory was actually right in every 10 years. As you said, it has taken 50 years, but processing, it's the way the things are being processed have literally changed every 10 years, almost.
And then we're going through a very interesting transition now, because if you look from mainframe to mini to workstation to PC to mobile, every one of those was something like, when you have 100 times more transistors, you can use only 10 times more and make a computer 10 times smaller, right?
Yeah.
So you went from megawatts to 100 kilowatts to 10 kilowatts to 1,000 watts to 100 watts, 10 watts to 1 watt. Right. And then we are now in the AI revolution, and these computers are way bigger than mobile. Right. And now AI turns out to be a very broad space, and it's unlike, if you look for a workstation, a PC to mobile, you can just look at those devices and say, a workstation is a big box, a PC is a small box, a mobile is in your hand. But AI is a revolution in, let's say, computation. And its natural place started in the high end. And then it turns out the bigger you are, the better you can train. So the big computers got even bigger, which is amazing.
Right.
But the AI researchers and modelers are trying to figure out, how do I bring AI computation to things as small as a mobile device?
Yeah.
But it's very different from the previous paradigm.
In what way? Because it is, every time when we talk about AI these days, everybody wants to talk about edge AI, but how is it fundamentally different?
Usually, just think about when you have a lot more transistors, you can make a smaller device. Like at some point when PCs got faster, it didn't make any difference, right? And when workstations got faster, it made some difference, but not a lot different. But when AI got faster, it made a lot of difference. And again, that's because a mainframe, workstation, mini computer, PC, they all ran C programs, right? Like we enabled graphics, like for a while when graphics was faster, it made a lot of difference, right?
Yeah.
So you have like your mobile GPU, which is very, low featured, in your PC, but we finally got enough transistors to make a really great mobile graphics thing. But when AI first started to work, it wasn't like we needed 10 or 100 times more computation. We needed 100 million times more, right? And it's very interesting because the next step was so big, right? Whereas to go from a PC to a mobile device, we had to go from a 100-watt computer to a 1-watt computer. That's 100 times less power. right? And we did it while adding transistors, right? So that
Yep.
was, but 100 times 10 is 1,000. It's not 100 million, right?
Right.
So when people started researching AI, they were running small programs on workstations, right?
Oh,
And then when OpenAI trained ChatGPT-4, they supposedly used 10,000 GPUs that were big, right? That was 100 million times more computation than the first AI program that ran on a workstation. That's a
and that's a
really,
huge,
really, so
huge, yeah.
so there's an expression that says a difference in quantity causes a difference in kind. Right. And the obvious example is if you see one ant, you can't imagine an anthill. Or if you study one neuron, you can't imagine Shakespeare, right? Like something happens between one neuron and 10 billion neurons that where you go from, neurons firing and things happening.
Yeah.
So I would say, yeah, I've had a really good career building computers. I have mostly not been like Gordon Bell's a visionary kind of guy. I know visionary people. I have applied things like Moore's law and Bell's law to what do I think will happen next,
Yes.
right? And when we designed Opteron, which was a big transformation in how we built PCs and servers, people said, but Jim, you don't understand. We'll never have enough memory. And I drew a curve on a board, said, here's the DRAM roadmap, right? And people always want to know what's going to happen next. And I just draw the line and I say, probably there'll be another dot, because after 30 years of DRAMs getting better every 2 years, I believe in Moore's law. And then Moore's law says I will be able to build a server with enough memory to be a very small form factor. It'll change how we do it, right? We did the same thing when we put a very large CPU in an Apple chip. And when we first decided to do it, people said, Jim, you don't understand. We'll never be able to get that processor to a low enough power to be super efficient as a phone. And I drew the curve, like Moore's law, Bell's law says, the first one, it'll be a little too big. The next one will be pretty good. 3 years from now, everybody will be shocked at how good the Apple iPhone chips are because we are following the technology, trends. We call them laws. They're
Right.
not exactly laws, but they're something. And so knowing what was going to happen gave us the right insights about what to do. And then actually doing it is hard. Like it takes a good engineering team and, we spend a lot of time on it.
Does that insight actually help? I mean, that, Moore's law, Bell's law, do they actually help you to think about this 100 million times
Yes,
increase
of
that we're
course.
seeing in AI world?
Yeah. And like, I'm CEO of a company that's building AI devices, and we are building technology because, some of our technical decisions are because I believe with the next couple generations of chip, I will get, a certain number of transistors on chips. The speed of the memory will change in certain ways. I need to a friend of mine told me the computer design is all about calling the ball 5 years in advance. So like when you do a computer design, it takes you a year to figure it out. That's one. A year to design it. A year to produce it. A year to validate it. A year to ship it. That's 5 years. Right? And then
Yep.
there's a new one every year. So like there's a new iPhone chip every year.
Right.
And some of the ideas that people are working on, like the most future, the most open ideas will be in a product 4 or 5 years from now. Right. And so then you have to guess what's going to happen.
Our guest was Jim Keller, CEO of Tenstorrent, AI processor startup. You just watched the first half of our 1 hour conversation. In part 2, which will be released shortly, our conversation goes deeper into Jim's view on the next generation computers and what he sees as the key building blocks that are bringing innovation to the AI world.